Today we want to talk about energy storage. Why do we need energy storage? It is to complement the fluctuating wind and solar power according to the actual energy needs. Why we talk about wind? In many locations, wind and solar power complement each other. We speak out of an anti-correlation, so less storage will be needed. For the moment, the energy storage is the most expensive part of energy transition towards 100% renewable energies. As a rule over the thumb, we can say storage is about 2 to 3 times more expensive than the renewable energy power generation. Let's take a look at the lecture. So we want to talk first about the storage parameters and its characteristics. We want to talk about storage technologies. We want to talk about mechanical storage. First, we talk about the mechanical hydro storage power plants. We also want to talk about compressed air energy storage. Then we switch over to the chemical storage. There we will discuss hydrogen storage, power to gas storage, lead acid batteries and lithium-ion batteries in particular. Then we switch over to electrical storage. There we want to treat the double layer capacitors, or more often known under the name super or ultra capacitors. At the end, we want to see an overview of the different storage technologies and their applications. But first, let's talk about storage characteristics. We have major parameter is the efficiency. That means what's the ratio between the actual output energy of the battery or the storage to the energy supplied before. With the power, that's the maximum quantity of power to be supplied by the storage systems. So it's expressed in watts or kilowatt or megawatt, whatever, depending on the size of your storage system. Then we have the storage capacity. So it's the electrical energy in kilowatt hours or megawatt hours or gigawatt hours inside the storage as a whole, or only the actual usable part of that energy. That's actually better. The storage capacity is essential for the storage layout and thus defines the actual costs of the energy storage. Then we have the energy density. The energy density, it's expressed in kilowatt hours or megawatt hours or terawatt hours in cubic meters or in kilowatt hours per kilogram. It describes the ratio of the usable amount of energy to the volume or the mass of the storage systems. For stationary systems, this has a minor role. It's more relevant for mobile systems. Then we have the charge or discharge time. So it's measured in seconds, is a period of time in which the energy storage can absorb or deliver a certain amount of energy. Often it's in relative terms, so in percent of the storage capacity. This extends from seconds, primary power control, to several days to balance out medium-term electrical storage, or can even months if you consider seasonal storage. Then we'll discuss about the self-discharge rate. So some energy storage lose energy even in standby mode. Self-discharge is given in percent per unit of time, for example in percent per month. Reason for that self-discharge are, for example, a leakage current, or if you have a thermal storage, heat losses or magnetic losses, or for example for a pumped hydro systems, evaporation. A very important characteristic is the storage cycle number. So it indicates the maximum number of 100% charge and discharge cycles. We also speak out of full cycles. During the lifetime of the storage device, lifetime is usually defined as a threshold when the storage system reaches below 80% of its initial storage capacity. For some application, this can be more than sufficient. Then you can put a lower threshold, for example, for stationary applications. The useful life of a storage device depends greatly on the usage profile, the depth of discharge, the rate of charge and discharge, and very important, operation temperature. The specific costs So we have the costs of each energy cycles expressed in euro per kilowatt hour or euro per megawatt hours, including the investments costs and storage cycle numbers and losses. So let's talk about the different storage technologies. So first we have the mechanical storage. So some examples as the flywheel or the pumped hydro storage, what we will discuss now. And then the CAES, that means the compressed air energy storage, which we also discuss. Then we come to the chemical storage. It's usually the batteries or rechargeable batteries, so lead acid batteries, lithium-ion batteries, or nickel-cadmium batteries. Then we have also hydrogen and methane storage. Usually the expression power to gas appeared the last decade. And finally, we have the electrical storage with the double layer capacitors, or sometimes the words ultra capacitors or supercapacitors is used for that. Let's first start with the pumped hydro storage plants. In principle, they are hydropower plants in which water is stored in an upper elevated reservoir and released to a lower reservoir. During the periods of high electricity demand, the stored water is released through turbines to produce electricity. Hydro storage power plants work the same way as river power plants, only the water accumulated in a reservoir to balance out fluctuations. This allows a better utilization of the plant and the turbines. That kind of power plant is often disputed while it may lead to large nature invention, for example, large flooded areas. The electrical working capacity, EL, of a storage power plant is given by, so we have the volume times the density times the acceleration of gravity times the height and times the combined efficiency of turbine and tubes and the generator. The height is also expressed as a height of fall in meters. The storage amount is the energy stored in a reservoir. The amount of electrical energy to be stored is the same, about the same. So we have the storage volume in cubic meters, the density of the water, which is 1,000 kilograms per cubic meter, the acceleration by gravity, 9.81 meters per second in square, the fall height also a meter, and the combined efficiency of the tubes, turbine, generator for the reconversion of electricity. If we derivate this from the energy to the power, then we have the derivation to time of the energy, and that is a derivation of the volume to time. That's the volume flow now in cubic meters per second. There is nothing to derivate at the density and also at the acceleration of gravity, also at the height. The same applies for the conversion efficiency. This is typically for large-scale power plant in the vicinity of 80%. We make a small example here. This is an actual storage power plant in Austria. The following data is given. So the upper storage limit is high up the mountains at a height of 2,036 meters. The lower limit is still at a height of 1,960 meters. The outlet is at the height of 1,672 meters. The storage limit is 85 million cubic meter. The area relevant for our input, this area where all rain will be collected in this reservoir, is 94 square kilometers. So all rivers which are in this vicinity collect the water and bring it to that reservoir. The precipitation is 2,000 millimeters per year or 2 meters per year. So that's the typical precipitation over that area. So this leads then to the volume which comes in, or the flow that comes in. So that's the area times the derivation of the height so that is 2 meters per year, and the area is 94 square kilometers or 94 million square kilometers. So we have a volume of 188 million cubic meter per year what we can use. That's about twice the storage volume V, so we can empty the reservoir twice a year. To simplify the calculations, we take for granted that the reservoir has a cuboid layout, so we can calculate the average height, h dash. So take the average, so this is 0.5 h1 plus h2, what we saw at the beginning, minus the outlet h3. So we have here 0.5 times 2036 meters plus 1960 meters minus 1672 meters. So that's 326 meters. The average energy content is E dash is M times G times H dash, and that is rho, the density, times the volume times G times H dash. And we use the water density of 1000 kilograms per cubic meter and the acceleration of gravity of 9.81 meters per second in square. So we have then 85 times 10 to a power of 6 plus 3 kilograms times 9.81 meters per second in square times the average height of 326 meters, and that is 272 times 10 to a power of 12 watt seconds, or if we calculate it in watt hours, that is 76 times 10 to a power of 9 watt hours. So if you calculate the average power available during 1 year, if we divided this by the number of hours of a year, that is 8,660 hours. So that's equivalent to a constant power of 8.6 megawatts. This constant power is not very useful. Usually the upper reservoir is filled up in the summer by the melting snow and empty during winter for the maximum load. The annual turnaround is about twice of the reservoir volume. Usually we operate the power plant at full load during 25% of the year, and then the power of the turbine is, so we have here 2 times factor of 4, then the average available power is 8.6 megawatt, so we come to this full load power of 69 megawatt. And that's the actual turbine layout, how it was made. It's another example, a stored hydropower plant in Brazil, Itaipu. This is a power of 14,000 megawatt or 14 gigawatt. It's an enormous lake reservoir in the average of 1,000 square kilometers. The height of the dam is 196 meters. So that's higher than the Cologne Cathedral or the Ulmer Münster. They are only 160 meters. So it is really high, almost 200 meters of height. Here you see the layout. Here you see a crosscut of that dam with the included turbines and generators. This generates an electrical energy of 93,428 gigawatt hours per year, or 93 terawatt hours. To put this in relation, about the German electricity consumption per day is about 1.5 terawatt hours per day. With the years about 600. So the pumped hydro storage plant, so you just, as I mentioned before, you actually pump the water up to the upper reservoir, and during periods of high electricity demands, the stored water is released, as in the conventional storage hydropower plants, and they produce electricity. So you have a lower reservoir and upper reservoir, and here you have a combined pump and turbine. This is only possible with the Francis turbine. If you use different kinds of turbine, for example, Pelton or Kaplan turbine, you have to have a separate turbine and a separate pump. So the amount of electricity that can be stored, this depends on the turbine and the generator technology, the size of the upper reservoir, and the height difference between the upper and lower reservoir. So this kind of power plants need about 1 to 3 minutes before full power becomes available. Then it depends on the size of the upper reservoir, but quite typically are 8 hours of reservoir storage, depending. For example, in Norway, there are reservoirs which are much bigger, so they can supply energy for even weeks or months. Although short-term power fluctuation cannot be compensated directly with a couple of seconds, pumped storage power plants are still much faster than any conventional power plant. So the fastest conventional power plants are gas power plants. They need about 8 minutes. The most modern ones, 5 minutes only. If you take a look at coal power plants, lignite power plants, they take up to 8 hours to come to full power or to be throttled. So they have a rapid start capability, so they can be used to smooth the residual load. They can be used to compensate for unexpected variation in power consumption. They can provide also control in the energy market. In Germany now we have currently about 30 pumped hydro storage power plants, which have together a power of 6.2 gigawatts. Many devices are small. They have a power of less than 300 gigawatt. The most powerful pumped storage power plants in Germany is about 1 gigawatt and a storage capacity of about 8.48 gigawatt hours. And it's located in Goldistal. I show you some pictures about that later. So this is just the principle here. You have here the lower reservoir and the upper reservoir. You have the turbines, and during time of low demand, and usually if you have low demand you have low electricity prices, so you take that advantage and pump water up to the upper reservoir. If there's high demand, usually also prices go up, and then you release that water from the upper reservoir through the turbines and generate electricity and make even profit if the price difference is high enough. This price difference is a bit of a problem in Germany. So if you want to use 100% of renewable energy, and that's in Germany basically solar and wind power, we have to have storage and compensation mechanisms to balance out the power availabilities during day and night and during periods of high wind and low wind. These devices are very useful, but at the moment, due to the low flexibility of conventional power plants or existing conventional power plants, electricity prices are really, really low, sometimes even negative, because the conventional power plants, for example, lignite power plants, can't react sufficiently fast enough. So from the point of the investor who wants to invest in such a power plant, it's rather difficult because, okay, he has low electricity prices, so he can pump up for cheap prices, but during high demand, the electricity prices are not sufficiently high to make such a system profitable. So here, close by to Paderborn in Höxter, there was a very well advanced plan of such a power plant, but it couldn't be realized because the business plan didn't work out, because the price difference between pumping and releasing hasn't been big enough to justify an investment. Here you see a power plant operating in the south of Germany, Säckingen. It's a quite interesting power plant. It works in a cavern, so you don't see anything of this power plant. And here you see the pumping here of the, so it purchases electricity in nighttime and releases it here during daytime. And usually this should be enough to justify the investment cost. So it works profitably during that period. Here there's a picture of that. So here you have turbine and pump, so quite a big device here. As I mentioned before in the scheme, you pump up water and release it during daytime. So this is not a Francis turbine, so you have two different turbine and pump separated here. So advantages of such pumped storage power plants are they provide system security presently, but even more important for future energy systems. They are also considered as a long-term energy storage because the losses by water evaporation are quite negligible. So this can be even used for seasonal storage, not only for daily or weekly storage. There's another example here, an island. So you see here the upper reservoir, and here the intake, and here the power plant and the discharge. What you see here, usually the power plant is a little bit lower located than the actual discharge. If you would locate it higher, there could be quite a low pressure here, and this could lead to some bubbles in the turbine, and there is an effect called cavitation. These steam bubbles can destroy the turbine blades, and therefore you always put the discharge a bit higher, so there's a counter pressure also on the outlet of the turbine, and this avoids this cavitation issue. Here is the Goldistal power plant. So same thing, so the outlet is here a bit higher to put some counter pressure, and here we have the cavern where all the equipment is here, the turbines and the generators and the pumps. Here the height difference is in between, depending on the height of the upper reservoir, between 325 and 280 meters. This size is only 29.5 meters, so the height of the upper reservoir, the internal height, and the volume here is 12 million cubic meters. Show you some pictures here. So this is a lower reservoir. It was formerly a river, but there was a dam built just to have a bigger size of the lower reservoir, and this is a total artificial upper reservoir. As I mentioned already, about 1 gigawatt of power and 8 gigawatt hour of storage capacity. We've been visiting that with some students from Paderborn. Here you see our excursion. It's quite a long journey, so about 5 hours drive one way. Here you see the explanation here. This man is explaining how this plant works. Here you see the grid here. So here the grid is directly connected to the high voltage transmission wires here. It's in Germany, the voltage of 380,000 volts. There's also some lower for the city here, mid voltage with 10 kilovolts to supply energy to the city of Goldistal. Here you see some typical loss diagram of such a power plant. So you have here the electrical input. So first you lose about 0.5% at the transformer. Okay, that's very small, that's negligible. 3% at the motor, about 10% at the pump, 0.5% at the tubing, depending on the size of tubing and the length of the tubes and so on. Then you have here the storage lake, and then you release it from the storage lake. You have again some tubing losses, depends on the velocity, on the diameter of the tubes and length of the tubes. Then about 8% at the turbine, so you see it's a bit lower than the pump losses. Then about 2% at the generator, again 0.5% at the transformer. They are remaining 77% as electrical energy output. If you take a look at other neighboring countries, there's also potential in Austria and Switzerland, but by far the largest potential is in Norway. The potential of some interconnected lakes in the vicinity of 7.8 terawatt hours. They're not gigawatt hours like Goldistal, but terawatt hour. This is 1,000 times more than Goldistal. So if there would be a good connection to that lake system, we would have power for about a week in Germany, or a bit less than a week, 5 to 7 days. This would be sufficient to supply energy even during times of low irradiance and low wind velocities. There is already a connection set up, but the maximum power to be transmitted through that connection is about 1.4 gigawatt. Could be really much more, just in the vicinity of 10 times more, 20 times more, would be very helpful to go on with German Energiewende. Here, just an overview. If you take a look at the data sheet of pumped storage, hydropower plants, you have an efficiency of 65 to 85%, power from 2.3 megawatts to about 1 gigawatt in Germany, to say, and storage capacity in Germany is 8 gigawatt hours. If you go to other countries, if you see Norway, it could be even 1,000 times more. Energy density is 0.35 to 1.12 kilowatt hours per cubic meter. Discharge time 5 to 10 hours, depending on the demand. If you have a really large reservoir, why not using it for weeks or even months and use it as a seasonal storage? Self-discharge rate, depending on the temperature, is 0 to 0.5% per day. The cycle numbers is almost unlimited. It depends on how long your civil engineering construction lasts. So usually this kind of plants are planned for operation times of 100 years. The specific investments costs are 100 to 500 euro per kilowatt hour of storage capacity. It's marketable. The oldest of such power plants are in operation for almost 100 years. New developed underground pumped storage is a new potential to do that, to reduce the environmental impacts. Even you can use this almost century-old factory for modernization. A problem in Germany are the limited locations, but as I mentioned, there are a lot of neighboring countries which have very favorable locations. Come now to the compressed air storage at CAES. So the principle is you have compressed air, then you release it during, you compress during periods of high availability of electricity, and you release it through air turbine during periods of low availability. As storage, it's too expensive to make artificial storage from steel tanks and so on. What you use is already existing caverns, depleted wells or aquifers. The compressed air can be released and run through turbines to generate power if wind turbines and solar plants reduce their power output and this power is needed. So already this is the definition of storage need. So here you see that. So you have here our compressor. This needs electricity, sure. You have here for low pressure and high pressure. During the compression process, there is a release of heat. If you pump up your bicycle with air pump, you feel it, it gets hot. And you can use that heat for the preheater, for example. So this means adiabatic use. This improves the efficiency, which is usually quite poor of such a CAES system. And here you have the storage, the cavern, use it, and this could be really high and therefore provide power for a long time, even if the air density is relatively low. What is often used here is a combination hybrid use with natural gas. So you're not only releasing the compressed air, you're also burning natural gas or methane, or it could even be hydrogen. That's not tested yet, but there is a possibility. So it could be even clean hydrogen and then go through a gas turbine with two stages, high density and low density, to increase the efficiency. And then you have the exhaust outlet and the generator, which supplies that electricity to the grid. So it could be used for a wide range of auxiliary service that are similar to those for the pumped hydro storage power plants. They provide control energy, for example, minute reserves. They smooth the load curve and long-term balancing compensation for windcast errors or solar errors. Usually windcast errors are more serious because if you make an error in wind speed, the output power is affected by the power of 3. By solar, it's linear, so if you make an error of 10%, you have an error in output power of 10%. For wind, it's much more severe. And all these applications serve to secure the stability of the power system. If you're able, for example, to smooth the load curve, then you're able to reduce the maximum power and transmission systems and so on. This could even lower the operation costs or even avoid necessary investments if you have an increased peak of a load. The CAES, they can react very quickly within a short time, so provision of full power within 8 minutes. So that's a bit less than the 1 minute or 1 to 3 minutes of a hydropower plant, but it's still much better than most conventional power plants. So they can satisfy a short-term need of energy, they can balance out short-term power fluctuations. The disadvantages, there are significant heat losses during the compression. I mentioned already some methods to avoid that or to use that energy. Usually efficiency is in the vicinity of 50%, so here a range of 40 to 54% is given. Large storage volumes required from 300,000 cubic meters to 700,000 cubic meters because the energy density of the storage is relatively small, considering a nominal pressure of 50 to 70 bar. If we compare that, for example, to a car tire, is about 2 bars. A bicycle tires is up to 9 bars for a race bicycle tire. Here our data sheet for our CAES application is for peak load control power efficiency 40 to 45%, or sometimes a bit higher, so we saw 54%. The only basically 2 power plants on the world existing, so this is 110 to 290 megawatt in Germany in Hundorf. There's another one in McIntosh in the United States. The storage capacity is here 580 megawatt hours. The energy density is 0.5 to 0.8 kilowatt hours per cubic meter, so significantly less than the one of pumped hydro storage power plants. Discharge time 2 to 24 hours, it could be even longer depending on the needs. Self-discharge rate similar to the pumped hydro storage power plants, 0 to 0.5% per day. Also cycle number is theoretically unlimited. Investment costs are 40 to 100 euro per kilowatt hour of storage capacity. Market stage is a marketable. Development potential are in the researchers' developments, optimization of conversion efficiency, a big issue, and also to make really large devices in the vicinity of a gigawatt.
The often overlooked technology of flywheels has been reinvented and may be a good fit for supporting renewable energy like solar and wind. High power density, long lifetime, high efficiency, and being carbon-free has boosted interest in flywheel technology. But how do flywheels stack up over other energy storage technologies? The world has been shifting from fossil fuels to renewable energy sources in order to achieve low carbon emissions and maintain cheap prices. Both electricity consumption and renewable energy generation have been increasing all over the world in the past few years. In 2018, global energy consumption reached almost 25,000 terawatt hours, and of that, solar and wind only accounted for about 1,827 terawatt hours, or about 5% of the total power generation in the world. Since renewables like solar and wind aren't available 24/7 and can't be turned on and off at any time, energy storage systems need to be placed together with solar and wind farms to make them more widely viable. But why do chemical battery installations get all of the buzz right now? Why not flywheels? I mean, the first question to ask is probably, flywheels? Really? Or maybe actually it's, what are flywheels? A flywheel contains a dual-function electric motor to store and generate energy. It operates like an electric motor in an EV to speed up the flywheel using electricity, so that kinetic energy is stored in the spinning wheel. Then when it's turned off, the dual-function electric motor operates like a generator, and the mechanical energy stored in the rotating mass spins the generator's rotor, producing electricity. It's similar to how regen braking works in an EV, but when it comes down to it, a flywheel can be considered a big mechanical battery. To get a little nerdy for a second and talk about physics, the rotational energy of a rotating mass is directly proportional to the moment of inertia, or rotational mass, and angular velocity. That's a lot. For example, imagine that you spin 2 car wheels of the same mass, one at 30 kilometers an hour and another at 100 kilometers per hour. Which one will be harder to break? You probably guessed the faster one. That's an example of angular velocity at work. Now let's say one of the wheels is 5 kilograms and the other is 10 kilograms. You speed them both up to the exact same velocity, so they're both spinning at 30 kilometers per hour. Which one will be harder to stop this time? If you guessed the heavier one, you got it. And that's an example of rotational mass at work. Optimizing the shape and increasing the rotational speed will boost the energy that's stored in a flywheel. However, speeding up the flywheel increases centrifugal forces it's subjected to, and the resistance of the material that it's made from limits the amount of energy a flywheel can store. The bottom line is, spinning a flywheel too fast can completely break it apart. Now that's obviously something you want to avoid, but as I mentioned earlier, this is something we've been trying to master for a long time. Flywheels were first used in potter wheels and spindles in ancient Mesopotamia to produce threads. Later, they played an important role in the Industrial Revolution, when flywheels were used in engines and machines to smooth out the power delivered by the driving device. However, the first flywheel used exclusively for energy storage was built by John A. Howell in 1883 for a military application. In this case, the flywheel was installed in a Howell Mark I torpedo and worked as a propulsion source and provided directional balance. In the 1940s, the concept of flywheels was used for transportation by the Swiss company Oerlikon when it released its carbon-free bus containing a flywheel for energy storage. The gyrobus used energy from the grid to spin up a flywheel system, which operated as a generator while it was on the move. And when the flywheel was completely charged at about 3,000 RPM, the bus could run for about 6 kilometers at speeds up to 50 to 60 kilometers per hour. Since then, several improvements have been made to flywheels in order to increase power storage capacity with safe operation. Flywheel energy storage systems, or FESS, are essentially composed of a few key components besides the flywheel and electric motor. It includes bearings, an enclosure, and a power electronic converter. FESS have bearings to support the rotor and resist against forces to maintain its position, which allows it to spin at the high velocities, but there's a downside there. Mechanical bearings require high-performance lubricants and frequent maintenance to operate properly, and they're also sensitive to friction that it generates, and that's one of the main losses for flywheels is the friction. To solve for that, expensive magnetic bearings are employed in flywheels that operate at high speeds in order to reduce maintenance basically to zero, since they don't require any lubrication at all. It also helps to increase efficiency due to their minimal losses. Flywheel energy storage systems fall into two categories: low speed and high speed. Low speed flywheels are made up of steel and spin at rates up to 10,000 RPM. These are heavy and use the advantage of their angular mass to increase their stored energy, much like I talked about before. Now, on the other hand, modern flywheels that feature high power density and efficiency can reach up to 100,000 RPM, which makes it store more energy since the flywheel energy is proportional to the square of angular velocity. You still with me? Because I'm not sure I am. Advanced flywheels are housed in a vacuum enclosure to reduce aerodynamic drag. They also have air or magnetic suspension bearing technology to reach those high speeds and are made of materials with high strength-to-weight ratios like carbon and fiberglass. In practice, flywheels have fast response to frequency changes, making it a good solution to stabilize grid frequency when unstable variations occur. In addition to that, they can be completely charged within a few milliseconds and have considerably longer lifetimes of about 20 years compared to other technologies. They're highly efficient at about 95% and have a high power density so it can store more energy in a smaller space. And it's because of those advantages that they've been used in things like uninterrupted power supplies for industrial and commercial applications to provide backup for essential loads. Flywheels have also been used as control moment gyros in spacecraft like the International Space Station to hold the space station at a fixed altitude relative to the Earth's surface. They've been used in motorsports for hybrid propulsion systems and regenerative braking, like the Audi R18 e-tron that won Le Mans in 2012, 2013, and 2014. And they've also been used in the electrical grid to support the increasing spread of renewables. FESS have also been used in grid applications in order to provide ancillary services, such as frequency regulation and power fluctuation support. It's similar to how Tesla's Hornsdale Power Reserve has been used in Australia. Some examples are the Beacon Power 20 megawatt units installed in Stephentown, New York, and Hazel Township, Pennsylvania to support frequency imbalances in the grid. These plants were commissioned in 2011 and 2014. Beacon's flywheel rotor is made up of a carbon fiber composite rim. Its flywheels spin up to 16,000 RPM and can completely charge and discharge for 175,000 cycles. Another company playing this game is Amber Kinetics. Their all-steel M32 model can provide 8 kilowatts of power for 4 hours, achieves efficiency higher than 86%, and offers 11,000 cycles. In 2018, the company, in partnership with West Boylston Municipal Lighting Plant, commissioned a 128 kilowatt, 512 kilowatt hour flywheel energy storage system in Massachusetts. This project is integrated into a grid-connected solar array and has already discharged 116 megawatt hours. Amber Kinetics also installed another storage system, but now in China, to operate a 60 megawatt solar power plant in order to store electricity and improve grid stability. Since it commissioned in 2018, it's already stored 75.6 megawatt hours with no gas emission. But how do flywheels stack up over other energy storage systems? Compared to batteries, flywheels are made up of environmentally friendly materials that can be reused, and they may have higher capacity than lithium-ion and flow batteries. In addition to that, batteries need to be recycled and replaced more frequently than flywheels, which have a much longer life cycle. In comparison to other mechanical energy storage systems such as compressed air and pumped hydro, flywheels reach higher efficiencies. So what's the catch with flywheels? Why haven't we been seeing them pop up in solar and wind farms everywhere? Well, the latest technology provides energy for just a few hours, and flywheels have high energy installation costs. According to one report in 2016, FESS costs varied from $1,500 to $6,000 per kilowatt hour. And expected installation costs by 2030 will range from $1,000 to $3,900 per kilowatt hour. On the other hand, lithium-ion battery storage systems for utility-scale applications varied from $200 to $1,260 per kilowatt hour, and is expected by 2030 to see a reduction to between $77 and $574 per kilowatt hour. Flywheels are also beaten out by flow battery technology, which may reach between $108 and $576 per kilowatt hour by the same year. Another interesting analysis is the levelized cost of storage, which is directly comparable to LCOE, but for storage systems. In this analysis, the mean for flywheels might reach around $520 per megawatt hour in 2050, while lithium-ion and vanadium redox flow batteries might have a mean between $280 and $220 per megawatt hour respectively. Flywheels need to have a big cost reduction and performance boost, along with the development of new materials with high strength and low density for rotor materials, as well as improvements to the motor and generator itself. This means a lot of money and time spent on research and development, which is why flywheels have been overlooked in favor of the latest battery technologies. But there is an interesting hybrid approach. But before I get to that, I'd like to thank Brilliant for sponsoring this video. If you'd like to learn more about physics and kinetic energy, check out the Science Essentials course at Brilliant. Physics was never really my strong suit, so brushing up on potential energy and kinetic energy really helped me wrap my head around flywheels. Even if physics makes your brain spin with angular velocity that's hard to stop, Brilliant has over 60 courses in other topics like mathematics, science, and computer science. They teach all of the concepts through fun and interactive challenges, which help you understand the why of something, not just the how. It helps to develop your intuition, which is my favorite part about Brilliant, and it taps into the way I learn. Go to brilliant.org/undecided to sign up for free. The first 200 people will get 20% off their annual premium membership. Thanks to Brilliant and to all of you for supporting the channel. Now back to the hybrid approach. Some recent studies and projects have been developed to verify the feasibility of integrating flywheels with batteries for hybrid energy storage systems. One example is the Adhystore project operated by Schwungard Energy that's already received about 3 million euros funding for building out a 1 megawatt battery flywheel hybrid energy storage system to support grid stabilization and road. Another recent example is the 8.8 megawatt lithium-ion battery that's been integrated with a 3 megawatt flywheel system in Almelo in the Netherlands. It's going to assist with the integration of green power sources to the grid. These all look to be promising solutions and show that flywheels, although they're an old technology, may be making a bit of a comeback.